Welcome, friends. So, in the last session, we have discussed the distribution system, introduction of distribution system, and a brief comparison between a transmission network and a distribution network. And at the last, we have seen the different types of distribution network depending on the supply, depending on the network, and of course depending on the loading. So in the next few sessions we shall discuss one by one with some problems. So let us proceed. So let us say we have a conductor like this. And from this conductor, the consumers are tapping power at different points. Let us say this is consumer 1. Let us say this is consumer 2. Let us say this is consumer 3, and so on. Let us say we have a voltage supply at this point. Let us say this is the point A, and the far end, this point is point B. So this conductor or feeder, this is called feeder. This feeder has a resistance. So this will inject some current into the feeder. This will inject some current into the feeder, and the loads will be tapped as per the individual requirement of the consumers. So the moment the current is flowing through this feeder, some resistive drop will occur. Resistive drop will be there. Okay. So the consumer 1 is at this point, and let us say we have a 50th consumer at this point. So naturally the 50th consumer will get less voltage than consumer 1, because the drop will be very drop of the voltage drop along the entire length of the figure will be a appreciable value. So the voltage at, let us say this point is Q, and let us say this point is P. Naturally Vp greater than Vq. So this is the problem. This is the problem with this radial configuration. It is, it is called radial configuration, as discussed previously, radial feeder. Now since the supply is given at one end, so it is called single end feeding. Radial feeder, single end feeding. Okay, radial feeder, single end. So what is the problem with this scheme? So the voltage or consumer sitting as the far end from the supply will get the lower voltage. As we have seen, the VQ is very less than that of VP. That is the problem. So how that problem can be solved? Let us say we have another feeder. Of the same length, AB. Okay, same length AB. And if we tapping power, or if we tapping loads, let us say this is consumer 1. Let us say this is consumer 2. Let us say this is consumer 3, and so on. And this is point A and this is point B. So now if we going to give supply from both ends, supply at point A and supply at point B. So this scheme is called radial feeder with double end feeding. So in this way, you see that since the voltage is being fed from both ends, so the minimum voltage comes something around at the mid position. Let us say this is so on, this is the 50th consumer. Okay, So naturally V1, or let us say if this is Vp, this point is P, and let us say this point is Q. Now if we consider another intermediate point, let us say R, so naturally VR will be less than Vp. In the same way VR will also should be less than Vq as well, so that this should be the minimum potential. So this is the consumer situated at the around some mid position of the length of the feeder will enjoy or will have the least voltage. However, this situation, that is the double end feeding, this situation is very much better situation than the single end feeding. Another scheme could be there that suppose if let us say VA, this VA and this, let us say this VB. If we assume that VA is equal to VB, okay, let us say if we assume VA is equal to VB, that means two nodes are being supplied at the same potential. That means you can say that this entire feeder can be looked in by a ring-like structure. Entire feeder can be looked into a ring-like structure. So this voltage is either VA or VB, since both are same. Now several tappings are, current load tappings are there in this way. So this is called ring main. This is called ring main feeder. Its feeder is like a ring-like structure. Why ring? Because we are giving two end supply at equal voltage. That is why it is something, or it is it is not like that ring is looking like a circle. No, because at the two end we are giving supply at the same voltage. That is why it is behaving like a circle, because these two voltages are equal. That means VA is equal to VB. Now these three are fundamental schemes of distribution scheme. Now we shall solve some problem with DC excitation. We shall solve some problem from DC excitation. Now let us consider this problem. We have a DC distributor AB. It is 300 meter long. So you see, this is 40. Then the next part is 60. So then the next part is 50 meter. Then the next part is 100 meter. And then next part is, so total is 300 meter. Now this is being fed at voltage, at some voltage which is not given for this problem. Now the load are tapping as per this diagram. So load is tapping at point C, let us say it is 30 ampere. Load tapping at point D, let us say it is 40 ampere. Now load at point E is tapping at 100 ampere and load at F is tapping at 50 ampere. So there are four loads. So this problem is all about the concentrated load. Concentrated load. Okay. And now it is said that if the maximum voltage drop is not exceed 10 volt, that means a total voltage between VA to B should be voltage drop. It should not be exceed 10 volt. So maximum, this is the allowable. Maximum, this is permissible. Find the cross-sectional area of the distributor, this conductor. It is, you have to find out the distributor. So there is a given value, it is the resistivity of the material is 1.78 into 10 to the power minus 8 ohm meter. This is the problem. So you need to find out the voltage, you need to find out the cross-sectional area of the conductor. Find out cross-sectional area of the conductor. Okay. So now this problem, you can clearly see it is the voltage is fed at one end only. Okay, that means from this end no voltage is being fed. So that means this section VFB, this section is effectively open circuited. This section is effectively open circuited. Let me use some other colors. Let me use, so this portion, this section FB is open circuited. So this current 50 ampere, whatever it is tapping, whatever is being tapped at point F or node F, that current should be flowing through the section EF. So this is nothing but 50 ampere. So again, if you come at node E, so this current is being tapped at 100 ampere. So whatever current is flowing in the section DE, it is nothing but this 100 ampere plus 50 ampere, it is 150 ampere. In the same way, this current, the current at section CD, this will be 190 ampere. And finally, the current fed by the generator or the supply voltage, it should be 220 ampere. So if I summarize the result, it should be, let us first evaluate, it is the current in the section IEF, it will be 50 ampere. Then we have the section current DE, which is equal to 100 plus 50, that is equal to 150 ampere. Then we have a section called CD. This current should be 150 plus 40, which is equal to 190 ampere. And finally, the injecting current from the supply, it is IAC, which is equal to 190 plus 30, that will be equal to 220 ampere. So now, what you have observed, it is said that total voltage drop is not to exceed 10 volt. So this is the statement of the problem or requirement of the problem. So as per the problem, we have VAB, or you can say that is VAF, it should be is equal to 10 volt. Because FB is open circuited, this section is open circuited. This section is open circuited. So what is VAF? So VAF is equal to VAC, then we have VCD, then we have VDE, then we have VEF, that means that should be equal to 10 volt. Now what is VAC? What is VAC? VAC should be equal to so therefore VAC should be equal to now voltage is equal to current into resistance, so it should be IAC into RAC plus what is VCD? It should be ICD into RCD, simple, plus what will be VDE? It should be similar way IDE into RDE, and finally we have VEF, so it will be IEF into REF, it should be equal to 10. So now what is IAC? IAC is 220. So let me write it down, 220 into, now what is RAC? Now R, you know the formula, rho into L by A. R is equal to rho into L by A. So now rho is, you see the rho is same. Rho is same for every, because the conductor is same. So you can write rho into L. What is L? That is 40 meter long. So you can write 40 divided by A. So you need to evaluate this A value, right? Now in addition with this, you must multiply this with 2. You must multiply this with 2 because DC distributor, it is always having a mention is that it is a two-wire. It is a two-wire. So current should be flowing through a go conductor and through a return conductor. That is why these both the conductors you should take into a consideration. That is why when resistive term is there, you should multiply this with 2 on account of one go conductor, another one is for return conductor. So that is done. Now next term, ICD. What is ICD? It is 190 ampere. 190 ampere. That should be multiplied by, again, this is rho into L. What is L? It is 60. You need to multiply with 2 by A. And then IDE. What is IDE? It is 150 ampere. 150 into rho, that is length is 50. You should multiply it with 2 for go and return conductor divided by A. And the last term IEF, it is 50 into rho into L. Now what is L here? L, I think it is 100. Yes, L is 100. So it will be rho into 100. It should be multiplied with 2 by A, and this whole summation of 4 term, that should be equal to 10 volt. So now if you take common, so you can see that it will be 2 rho. Now rho value is this 1.78 into 10 to the power minus 8. That divided by A. It is common for every expression. Then within the bracket, it should be 220 into 40 plus 190 into 60 plus 150 into 50 plus then 50 into 100, and that should be equal to your 10. So now if you solve this expression or equation, you will get A is equal to 1.16 into 10 to the power minus 4 meter square, or you can write 1.16 centimeter square. So this should be your answer. So cross sectional area should be chosen at this value 1.16 centimeter square, so that voltage drop along the feeder or distributor is not exceed 10 volt. This is the solution for the problem. Again, now next we shall move to our next problem. Now it is both double end feeding. It is the double end feeding. The statement is quite similar. It is a two-wire distributor. it is 300-meter long, the same configuration. Now it is being fed at both ends. So VA is 225 volt and VB is 220 volt. So VA is fed at 225 volt and VB is equal to 220 volt. That means VAB, that means the potential drop, it is equal to 5 volt. It is the potential drop between A and B is 5 volt. Now the various loads and their position are shown. It is same value. Now the conductor resistance of both conductors is 0.2 ohm. Resistance is 0.2 ohm per kilometer. So this is given. Now you need to find out the current in each section and voltage at each load point. Current in each section, voltage at each point. Now to solve this problem, it is customary that, or it is expected that you should assume a current entering from supply 1 to this point is I. You can assume this assumption from this side as well. Now because this side voltage 225 voltage is greater than 220 volts, so we are assuming a current is being supplied from A node to the conductor in this direction I. So at node C, if the current is 30 ampere is leaving, so in the next section the current should be I minus 30. So we can write in the section IAC, the current should be I, and the next section ICD, the current should be I minus 30 ampere. Similarly, if we proceed IDE, the current should be another 40 ampere is stepping, so it should be I minus 70. So it should be I minus 70. Moving on, if we further extend, then next section would be IEF. That will be equal to I minus. So this current is at node E, the current is 100 ampere. So in the next section, the current should be I minus 170. And the next section or the final section FB, the current should be I minus 220. Now unlike the previous problem, now the FB section is not open circuited because the supply is being given at the both terminals, so a definite current will be flowing. Now this is your initial assumption. You must start with this assumption. Okay. Now similarly, now you can write the expression. You can write the expression. Okay. So what is that? So as per the problem, so your first part is AC. So your first part is AC. So for AC section, so you should write your equation as 2 into 0.2 that multiplied with I into 40. I explain each term. It should be R into I, right? So, okay, let me write it down in this fashion. 2 into 0.2 into 40 into I. So this 0.2 into 40 is the total resistance of this section A into C, right? This section A into C. From A to C, it is the total resistance, because resistance is 0.2 ohm per kilometer. Sorry, you need to make this one as 0.2 ohm per meter. So it should be into 10 to the power minus 3. It should be 0.2 into 10 to the power minus 3. 0.2 into 10 to the power minus 3 into 40 into I. That will be okay. Now this is for section AC. This is for the section AC. This entire expression. Now the next expression. Now the next thing is for section CD. So what will be the expression? The expression will be 2 into 0.2 into 10 to the power minus 3, and that multiplied with 60, because this length is 60 meter. And the current flowing is I minus 30. Should be I minus 30. So this is for section CD. This is for the section CD. The next term will come for the section DE. The next term will come for the section DE. Now similarly 2 into 0.2 into 10 to the power minus 3. Now in this case length is 50 meter. For section DE the length is 50 meter and the current is flowing I minus 70. So this section is for DE. This is for DE. This is for DE. So the next term is for the next term is for section EF. 2 into 0.2 into 10 to the power minus 3, that multiplied by 100, that is into I minus 170. So this is for section EF. The last section we have, 2 into 0.2 into 10 to the power minus 3, that multiplied with, that length should be 50. Length should be 50. So it should be multiplied with 50 and the current should be I minus 220. So if you sum these all 5 terms, it will give you the total voltage drop between VA minus VB, which is equal to 5. Is equal to 5. So if you solve this, as per my solving, please verify this please verify this equation or verify the answer. The current I, if you solve this, the current I should be is equal to 111 ampere. this answer. If you solve this big equation, it will get this solution. I should be is equal to 111 ampere. So that means what? Please verify. You are all requested to verify this result. Verify yourself. So as per this result, so I now let me go back to this section. Let me go back to this section. Our original assumption. Now see, IAC is actually 111 ampere. So ICD is what? ICD is what? Is 111 minus 30. That means it should be 81 ampere flowing. Now IDE, it should be 81 minus 70. That means it should be 11 ampere. How 11? Because this is I minus 70. So it will be 81 minus 70. That means is equal to 11 ampere. Now IEF. It is now 111 minus 170. That means this current now, you see, very interesting, minus 59 ampere. That means in the section EF, the original our assumption was current was flowing from E to F, but it is not that so. The actual direction of the current is flowing from F to E. This is the actual direction, F to E. It is flowing from F to E. And lastly, we have EFB. It is 111 minus 220. So it will be minus 109 ampere. So that means what? It should be flowing from B to F. So if we draw this entire network once again, so these are the various points A, B. Now this is C, this is D, this is E, and this is F. So current flowing from A to C, it was 111 ampere, and this current was tapped at 30 ampere. Now ICD was 81 ampere. So D, at point D, the current was tapping at 41 ampere. I think it is 40 ampere. So it should be 41 ampere IDE. I have made one mistake here. It should be 41 ampere here. I need to correct this. So IDE is 111 minus 70. That means it should be 41 ampere. Now as per this convention IEF, now it is 59 ampere flowing from F to E. So this should be the direction. So these two makes equals, these two current makes, this one as 100 ampere and this current was 109 ampere from B to F, and this makes, this is equal to 50 ampere. So this is the entire current loading of this scheme. Now we have left with another part, that is the voltage at each load point. So what should be, how should be calculated? Now this is VC. How? VC is nothing but VA minus voltage drop at section AC. Simple. So what is VA? VA is 225 volt minus what is voltage drop at V? This should be, that is equal to 0.2 into 111. So if you evaluate this, it will be coming out to be 202 point, sorry, it should be 2 into 0.2 into 10 to the power minus 3, that multiplied by 111. So you will have some value. Please calculate that. So now what will be VD? VD is equal to whatever is value of VC, that is minus with VCD. So that is equal to VC minus 2 into 0.2 into 10 to the power minus 3, and sorry, this should be multiplied with this length 40 meter, and this should be multiplied with 60 meter into the, what is the current in section CD? It should be 81. So in this way you should evaluate the whole voltage at each load point. Similarly, VE should be VB minus, okay, let me first evaluate VF. Let me first evaluate VF. So VF is equal to VB minus the current inflowing VBF. So VB is equal to 220 volt minus VBF is equal to 2 into 0.2 into 10 to the power minus 3. The length of BB section is 50 meter. Length of BB section is 50 meter. So it should be multiplied with 50 into the current flowing through this section is 109 ampere. So whatever value you will get, this is VF, and similarly VE should be is equal to VF minus VFE. That is VF minus 2 into 0.2 into 10 to the power minus 3, that multiplied by 100, because 100 is this length in the section EF, and that multiplied with the current flowing through this section is 59 ampere. So this should be your answer. So I request you do yourself this calculation. So this is the example. So these two problems essentially shows you the example of single end feeding and double end feeding. Okay. So with this I conclude this lecture here. From the next part we shall start discussion on, it is uniform loading. Thank you.